Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
I'm going to be talking today about some familiar things, which are fluids, things we interact with every day, and flexible bodies, like a sheet of paper, for example. So let's start by asking, what is a fluid? And perhaps you've seen it posed this way. Three familiar phases of matter. There's solid, liquid, and gas. In a solid, typically the molecules are arranged in some orderly pattern, perhaps like a crystal. You could think of solid water, which is ice. In a liquid, which is what we get when we heat up a solid and it melts, the molecules will start to move around each other. They'll leave those orderly positions, and they'll be in a state of continuous motion. And this will allow them to deform and take the shape of a container that they're in. And then if we heat this liquid up at a certain temperature, it will vaporize, turn into a gas, and then the molecules will actually fly away from each other. They'll have enough energy to break the bonds that keep them near each other as when they're in the liquid phase, and they'll actually fill up the volume of the container that they're in. And so fluids are actually liquids and gases. This is sometimes confusing point. A lot of people think fluids are the same as liquids, but actually gases are also fluids. And why is that? Well, we define fluids by how they respond to forces. So what I have down here in the lower left are a couple of diagrams of forces shown by the symbol F and the arrow. That's a force in the direction of the arrow acting on a solid and a fluid. And so if I imagine I have that little square of solid and I apply a force on the top surface in that direction, the solid is going to bend, it's going to shear, we say, into that dashed line shape, which is a parallelogram. And it will come to a rest under a constant force with that shape. Now we're assuming it's clamped at the bottom. The fluid, by contrast, if we apply So now what I'm imagining is I actually have a layer of fluid that occupies the space between two parallel plates. There's a plate on the bottom and a plate on the top parallel to it. And I apply a constant force to that plate on the top. Plate on the bottom is still fixed. And then the fluid is going to start to move. And unlike the solid, it's going to keep on moving. It's not going to come to rest. But what it will do is it will move, it will accelerate, and then it will reach a constant velocity, that top plate, if I apply a constant force to it. And what velocity will that plate be moving at? And that's also the velocity of the fluid that's stuck to it on the bottom surface. Well, that velocity depends on the fluid. If I have a very viscous fluid, it's going to move slowly. So you could imagine honey or mineral oil. And if I have a less viscous fluid like water, and I apply that constant force, it's going to make the plate go faster. And a similar principle holds if the fluid is a gas. So if you move the top plate and there's a gas confined in this gap, that will also put a force on the plate. And the force it puts on the plate and the velocity that the plate moves at is related to the viscosity of the gas. So air is a familiar example. Air has a certain viscosity, just like water does and just like honey does. So some general background here. So fluid dynamics is the study of how fluids move under forces. And this is a way that a fluid dynamicist might see their work in relation to other fields of science and engineering. A fluid dynamicist is by nature an interdisciplinary person because fluid dynamics shows up in all of these diverse fields. Astrophysics, The motions of galaxies can actually be described by fluid dynamics. You can think of the constituents of a galaxy, the planets and so forth, as elements of a fluid, particles of a fluid, if you will. And the motion of an avalanche, which is a phenomenon in geophysics, that's also the motion of a fluid. More familiar examples might be the circulation in the oceans on the planet, the circulation of the atmosphere and weather patterns. That's fluid dynamics. And also the motions of layers of magma inside the Earth. So a fluid dynamicist could be in any of these areas of research and in any of these departments in a university. And I haven't actually mentioned that they could also be in mathematics. So fluid dynamics relates to areas of mathematics like differential equations. It relates to topology and solving equations on the computer, which is an important area of applied mathematics. Okay, so now let's just think a bit more about the mechanical side of fluid, because that relates it to physics in particular. And so within mechanics, we can make a list of different topics, starting with classical mechanics, originating with Isaac Newton, the motion of particles and rigid bodies, celestial mechanics, motions of stars, planets, under gravitational forces, and here we have a constant g, which governs the gravitational interaction between bodies. Quantum mechanics, which deals with the motions of atoms, clusters of atoms, and subatomic particles. And here there's a constant that's a little h with a bar through it, which is Planck's constant, which governs interactions between those particles. Statistical mechanics governs properties of large numbers of particles interacting, such as in a gas or in a fluid. And then continuum mechanics, that's where we normally place fluid mechanics. So we think of a fluid as a continuous material that fills a certain region of space, and that actually helps us write down equations for it. We can think of fluid flow as a quantity that changes smoothly as we move around in space. And so we're kind of looking at the fluid on a larger scale than the individual molecules that are moving around, but we look at it on a scale where we can think of fluid velocity as having a continuous value as we move around in the region occupied by the fluid. And then there are other areas where the same principles apply: solid mechanics, electrodynamics, thermodynamics. So for fluid mechanics, I've put that symbol mu, which was on the last slide, 2 slides ago actually, which was the viscosity. And that, if there's one parameter that's maybe the most basic for fluid mechanics, I would say it's the viscosity for the physics of how fluids behave. But then, of course, there are many other parameters that do come into play. Okay, so a thing to note about fluids is that the same principles actually can apply over a very wide range of length scales. So we can apply the equations of fluid dynamics to the swirls of the clouds in the atmosphere. You can see on this image of Earth, there are these swirling patterns. That's described by the equations of fluid mechanics. And the scale of the Earth is about 6,000 kilometers is the radius of the Earth. So those fluid motions exist on a very large scale. And the very same equations can actually apply on a much smaller scale. So on the right, I have a picture of what's called a microfluidic chip. This is used for sequencing DNA, which is a very important application these days, and also doing certain functions in cell biology, probing the mechanics of cells on small scales, exposing them to certain treatments. And the typical size of the channels, so what that chip is, you can see there are these lines etched in it. And what those are actually very thin channels through which fluid flows, carrying DNA in cells and other things we're interested in studying on small scales. And the size of those channels is typically about 5 × 10⁻⁶ meters. So that is very small scale. You can see how it compares to the size of that dime there. So, the principles of fluid dynamics apply over the whole range of these scales, from the very small microfluidic cell to the size of the Earth, and in fact, even larger scales, the size of galaxies. So one thing that often happens when you have a fluid moving is you get these things called vortices. And that's basically the fluid develops a rotation or a swirling motion. And that can arise in a variety of situations. And it's just a very general phenomenon in fluid dynamics. It sort of arises naturally when you try to solve the equations. So on the left, I have an image of vortex shedding off the back of Socorro Island, which is in the Pacific Ocean near Mexico. And what you're seeing there are the clouds above the island. So you have an airflow past the island, and the island is disturbing the airflow. You can imagine it being like an obstacle for this large airflow over the island. The island is about 10 kilometers wide. And you can see the trace of the disturbance in the airflow in how it makes the clouds start to swirl behind the island. And there's actually sort of a regular pattern there. So you can see there's sort of a bending in the path of the clouds here, and then there's another one here, which looks kind of similar, and then there's another one out here. And so this kind of regular pattern arises often in fluid flows. Here's another example of exhaust from a plane. And so the plane is shooting out a straight jet of vapor and burnt fuel, and that straight jet eventually starts to acquire this wavy shape. And the principles of why that happens are very much the same in these two cases, even though the typical sizes of these objects are very different. Okay, so vortices are something that help us quantify fluid flows, help us think about fluid flows and compare them. Another important area to me in fluid dynamics is swimming and locomotion of flexible objects and deforming objects in fluids. A familiar example is a person swimming through a fluid. A person goes through a sequence of shape changes. They move their body around in a certain way to propel them through the fluid. And very small organisms, they also swim through fluids. So you can think of, in this case, we have sea urchin sperm. And so it's swimming through a fluid. And this is showing the flagellum of it. And so the flagellum is basically a tail that it waves, and it moves it in sort of a traveling wave pattern, which propels it through the fluid on a very small scale. So the typical, and then we can go even smaller. This is a paramecium swimming through fluid, and it's coated with a lot of little hairs called cilia. They propel it through the fluid, and the typical size of this is micrometers, very much like that microfluidic cell I showed before. Okay, so there are some common fluid dynamic principles that describe how these organisms move and how people move through water and how fish move and other organisms. And there, you can also think about how objects move on the surfaces of water. So rowing and motion of boats in general in water deals with surface phenomena. How waves are generated at the surface is an important aspect of the efficiency of a rowing motion. And then there's this interesting creature called the basilisk lizard that can actually run across the surface of the water without falling in. And it does that by basically slapping the surface of the water hard enough with its feet to support its weight on the water. So it can run across a pond, in fact, without falling in. Okay, so now I'm going to specialize a bit to the idea of fish swimming. So now we have something swimming inside the water. And the basic principles of fish swimming are actually kind of similar to that of other types of locomotion. So you can think about walking and running of people and animals on the surface of the earth, on the ground. And when we walk through the earth, we walk across the earth, we're applying a force to the earth, which is propelling us forward. And in some situations, running, for example, you can actually think about people running as sort of like a pogo stick. So we actually have a certain amount of springiness in the tendons in our body. And when we're running, those tendons can actually store elastic energy that's then released when we take another stride. And so fish can actually use some of these similar ideas in a fluid. So they're not actually pushing off of the ground, they're pushing off of a fluid, which is something which does very different motions, as we've seen. But nonetheless, whatever force they apply to that fluid is going to push them in the forward direction. And so we think that fish have evolved to apply these forces in a very efficient way to move themselves forward. Some fish have to swim thousands of miles in their lifetime, and so they probably don't want to waste energy doing so. And so what happens when a fish applies forces to the fluid? Well, you develop vortices. So again, we see this swirling motion that arises very often in fluids. And in this case, the vortices look kind of like a sequence of donuts. These blue donuts they're called vortex rings. And so what you can think of those vortices as looking like is basically there's swirling going on all around the donut as you go around it. And they're actually linked in this kind of configuration. So when you think about an object moving in a fluid like this, you get vortices, and the shapes of those vortices can be a bit complicated because of the three-dimensionality of the object. And I'll just note that insect flight actually has some similar principles. Insects fly in the air. Air is a fluid. And the same equations describe a lot of how insects get lift when they flap their wings in a fluid. So a fish flapping its tail fin and an insect flapping its wing produce a lot of the same phenomena in fluids. Okay, and so a lot of research in this field deals with things like what are efficient swimming motions for fish or simpler bodies? What's the role of body and fin flexibility in terms of storing elastic energy and releasing it at the right time? And how do fish interact with vortices? And this is particularly a situation in schooling. You've got multiple fish swimming together. Vortices from one fish are going to collide with another fish. And maybe, well, this is also a situation that happens when fish swim in a stream. When you've got flow in a stream, there are rocks and irregular boundaries, and vortices are created from those objects. And fish interact with those very often to save energy when they're swimming, or to position themselves in the right way to catch prey. So, okay, so there are various issues we can think about with fish. So one of the most basic ones is, why do fish undulate their bodies? That's perhaps the most common type of fish swimming. You see a fish undulating its tail and its body. And so a group at MIT built a robotic fish called the Robo tuna. It's in the shape of a tuna, and they suspend it into the water through this shaft that's sticking off the top of the tuna. And then they have motors which make the Robo tuna bend in the same way as a tuna. And they put it in a flow tank. So in this tank, they can generate a flow of water at whatever speed they want, basically, going past the tuna. And then they look at what happens. What's the flow doing, and what's the force on the tuna as it's doing this motion? And what they basically found was that when the tuna does this traveling wave motion, the flow going over the tuna remains attached to the body. So typically what will happen if you have a flow past a large body like this Robo tuna is that you'll get a lot of vortices coming off, and there will be a lot of drag on the body. But if the body undulates in this way, it can actually prevent so many vortices from coming off, and it'll achieve a much smaller drag in the water. Now, this experiment is a little bit different from an actual tuna, because the thing is, this Robo tuna is not swimming freely. Okay, it's suspended from this fixed post, and then it's doing its motion in a fixed position as the water flows over it. but an actual fish is swimming around freely in the fluid, and that actually alters the forces on it in some important ways. Okay, so what I did with my collaborators was to study an aspect of undulatory swimming using a simpler body, which does have some freedom to swim through the water. So one thing is the geometry of this Robo tuna makes things very complicated to understand. You can visualize the flow past this object, but it takes a lot of people, a lot of time to do that and try to process the results. And so when you look at a simpler body, you can understand things a bit more readily. Okay, so here's the simpler body. So instead of that Robo tuna, I'm thinking about simply a rectangular sheet of plastic. It's a thin sheet, so it has flexibility. And it's mounted on a shaft, like the Robo tuna was. And so what I do, though, is I move it in a very different way from how they moved the Robo tuna. And by the way, these experiments were done by my collaborators in a lab in Harvard's biology department. So this shaft is moved into and out of the frame of this picture. And so we can see that a bit more clearly if we look here. This is a bottom view of the shaft. Okay, so what's going on here? There's a rectangle which is immersed in a tank of fluid. And I'm calling that rectangle a foil or a flexible foil. It's we sort of think of it like an airfoil. It's something that can generate thrust forces and lift forces. And so there's a shaft which is holding it in this tank of water. Otherwise, it would sink to the bottom of the tank. And that shaft is mounted onto this sort of complicated-looking device, which is called an air bearing. And what does the air bearing do? Well, it allows this sheet to slide forward and backward with very little friction. So it's as though this sheet is free to swim in one direction, forward and backward. Okay, and so what we do is we take this shaft and we oscillate it from side to side in that tank. And if I look from the bottom, which is this view, oscillating it from side to side is this up and down motion that I'm calling a heave or heaving motion. So heaving means oscillating the leading edge of this plate up and down in a sinusoidal pattern. And if I just do that oscillating, holding it in place, what does it typically look like? Here's a snapshot where the white line shows the bottom edge of that sheet. It just adopts a kind of messy looking shape. It sort of flops all over the place. And it doesn't really do anything that's very easy to describe. But now what happens if I turn on the air bearings? If I turn on the air bearings, that makes this apparatus free to slide with very little friction. And that allows this rectangular sheet to slide forward and backward with very little friction. So now I do that same heaving motion I did before, but now the rectangular sheet is free to slide forward and backward. In this case, it was just clamped down in the forward-backward position, so it couldn't slide. But now it can slide, and it adopts this very nice traveling wave shape with these peaks that have a very constant amplitude as you move back along the body. And this is a movie of what it's doing. The movie is a little bit dark, but you can see, hopefully, the bottom edge of that object as the shaft is being oscillated up and down. So here's the shaft going up and down. And what are all these little points of white? These are little particles that have been put in the fluid so we can visualize what the fluid is doing, how the fluid's moving around this object. So it starts making this wavy pattern, and then it'll also start swimming forward as it does this. So that's why I say it swims spontaneously. If I just shake the leading edge of it up and down with this heaving motion, it starts to swim forward spontaneously. And that's what's going on here. Okay, so you can think of this as sort of like a very simple fish-like object. And it's simple enough that we can understand a bit more about how it swims. We can find out how the swimming speed depends on the stiffness of this plastic sheet. That's called the foil rigidity, and the length of the sheet, and other basic parameters like the frequency at which we're oscillating it up and down. Okay, so to figure out how the swimming speed depends on these parameters, length and rigidity, I did some computer simulations. So I took the equations of fluid dynamics, which I'm not showing here, but they're not actually that complicated. And I solved them on a computer for a certain type of situation, which is what we have here, the flow past a thin body. So here's a cartoon of a flow past a thin body. Here's the body. You can think of that as the plastic sheet. And then this dashed line behind it is called a vortex sheet or a vortex wake. And that's basically a sequence of little vortices that come off the trailing edge of that body as it's moving through the fluid. So the nice thing about this model is that I'm essentially computing the motion of one-dimensional objects in a 2D fluid. So the body bends as a 1D line in a 2D fluid, and this vortex sheet rolls up as a 1D line in a 2D fluid. And despite the simplicity of this model, it actually does the same thing as real fluids. So here's an example of an experiment. This is called a vortex gun. Basically, you can create a vortex in the water by doing this. You have a circular piston tube, and this is showing a cross-section through the tube out near the opening. And then when I push the piston forward from left to right, it expels water from that tube. And as the water comes out, it basically draws in water that's outside the tube and makes these nice vortices. And this is just a cross-section through the flow. So what actually is going on is there's a ring of vorticity that completes these two vortices that you're seeing. So they're actually part of the vortex ring that's going around. And so that ring has certain properties, and we can study those, and that helps us understand some things about vortices. And so what's shown down here is a computer simulation of the same phenomenon. This was actually done by a grad student and a professor here in the math department, Robert Krasny, in '94. And so here we have simulating flow out of a piston tube. And this black line is showing a sequence of vortices that are coming off the edges of the tube. OK, so I'm actually thinking of this tube as kind of like this thin body here. Whoops. They both have sharp edges off of which vortices are coming as the flow goes by. So this green line is showing the direction of the flow. You get vortices coming off this sheet. And here you've got vortices coming off the edge of that tube. And likewise in the simulation. OK, so this is an illustration of the kind of model I want to use to understand how that plastic sheet swims through the fluid. And the model works well for fluids with small viscosity, which is air and water, but not honey, for example, for which vorticity remains concentrated along lines. So that means that all the vortices that are in this flow just lie along this line here. OK, so here's some simulations of flexible foils with different lengths swimming through a fluid. The one at the top is the shortest, and they get longer as you go down. And they all adopt a pretty similar wavy pattern, except at the very bottom, it gets so long that the waviness starts to become irregular, and it does more of a chaotic motion. And I just want to give a little evidence that this agrees well with the experiment. So for one kind of plastic sheet, I'm showing how the foil moves in the experiment, just 4 snapshots, and how it moves in the model. And there's a similar amount of waviness here. OK, and so the value of these simulations is that they show, first of all, that there are resonances that happen in this system. So if I oscillate that sheet up and down at a certain frequency, I'll get a much faster swimming speed than if I'm at some other frequencies. In fact, there's a whole sequence of resonances. And they also help us find some analytical solutions to what the fluid is doing and what this flexible sheet is doing. And with those analytical solutions, we can get power law scalings for the swimming speed u versus the stiffness of the sheet B and the length L. And so this is what the power law scaling looks like. U goes like stiffness to the 2/15 power and length to the -1/3. So if I want a sheet to go faster, I should make it more stiff, because this term gets bigger as it gets stiffer. And I should make it shorter, because as it gets longer, as it gets shorter, this term increases. So Okay, and so a test of whether this relationship is true is to take some data from the experiment. That's what's shown here. So I have swimming speed versus length for 5 different foils with different stiffnesses, B. And so you can see that the swimming speed has some peaks, and then it has some troughs, and then some other peaks. The peaks correspond to these resonances. And so what I do is I take this velocity, and I divide it by the stiffness to the 2/15 and the length to the -1/3, and then it makes this data line up nicely, as shown here. The orange data is actually off of the chart because it has some very different properties. It's a much more flexible sheet, so it appears far off to the right. But for these 4 lines that are close together, it actually makes them line up quite nicely, and that's a test that the theory is actually explaining what the experiment is showing. Okay, so now I'm going to switch gears a bit and talk about falling of objects in fluids. And so this is one of the important concepts in how objects fall through the fluid is terminal velocity. So if I drop a penny through the air, it will accelerate up to a certain speed, and if it hasn't hit the ground yet, it will eventually tend to a certain equilibrium speed as it's falling. That's called the terminal velocity. And the same thing happens if you drop a heavy object in water. So over here, I have a demonstration. Okay, so we have a tube filled with glycerin. Glycerin is a liquid that's a lot more viscous than water. And what that's going to do is, well, when I drop things into the fluid, they're going to fall down. But since it's glycerin, they're going to fall a lot more slowly than they would in water. The viscosity is about 1,000 times that of water. Okay, so here I have a marble. So it's glass. And glass is more dense than glycerin. So when I drop it in, it's just going to sink down to the bottom pretty quickly. Not as quickly as it would have in water, but still pretty quickly. And so if I drop a penny, which is another pretty dense object, that will also fall down pretty quickly in the water, although not quite as quickly as that piece of glass did. And you might have also seen that it actually fell down with its flat side facing down. And that is actually a typical behavior of a thin, flat object like a penny. When it falls through a fluid, it prefers not to be edge-on, but it prefers to fall with its flat side facing the fluid. Okay, so now I can drop some other, so here I have another disc-shaped piece of metal. I drop it in the fluid, and you notice there's a fluttering motion now. Very regular oscillation back and forth from side to side. And this is also a very typical behavior of objects that fall in fluids, particularly if they're flat. So here's another flat metal disc. You can see that does some kind of very rapid fluttering with a higher amplitude. Okay, so we get these different behaviors when we drop objects in fluids. And the first one to explain is just the terminal velocity. What speed does it fall? At what speed does it fall through the fluid? So that is explained by this balance of forces. So we have as this sphere or whatever object you have falls through the fluid, there's a force upward, which is the drag force. So the fluid is slowing it down as it falls. And then there's also this buoyancy force, or buoyant force, which is pulling it down. The buoyant force is given here. It's the difference between the density of the particle and the density of the fluid. So that force is only going to go down if the particle is more dense than the fluid. Otherwise, if the particle is less dense than the fluid, it'll rise up like a bubble. And so it's equal to that difference in densities times gravitational acceleration times the volume of the particle. Okay, so the fluid drag force, depends on what's going on in the fluid. And here's a typical expression for the drag force. There's this thing called the drag coefficient, which I'll say a bit about in a moment, times the area of the particle. So you can think of that as the area of the sphere, the area that you would see as you look at it from below. The density of the fluid, and the settling velocity squared. So, and then there's a factor of 2. Okay, so typically for something falling in water, that force is going to be proportional to how fast it's going through the water squared. So if I set these two forces equal, the drag force going up and the buoyant force going down, I can solve for the settling speed, and I get this expression. And so the more dense the object is than the water, the faster it's going to fall, which makes sense. So there is this thing called the drag coefficient, which I didn't say too much about, and that is a constant that depends on the shape of the object. And the constant's around 1 in magnitude for a fluid of low viscosity like water. If you get to a fluid of higher viscosity like glycerin, then it adopts a different form that depends on exactly how viscous the water is. Okay, and so the fluid is slowing this thing down. And a way that you can see that happening is in the presence of vortices behind the object. So here are flows past a cylinder, actually. So if you imagine you just have a long cylinder falling through a fluid, as the flow rushes past it, if the fluid's very, very viscous, it's just going to go around it smoothly like that. If the fluid gets to be less viscous, though, then we move to the right here, and we get vortices. The vortices can either stay stuck to the object as it falls, and that's what's shown here. We have vortices which are stuck to an object, which is a sphere, as it's falling through a fluid. Or the vortices can detach from the object and make a regular array of vortices in the fluid, which is called a wake. So the drag is basically related to these vortices. There's energy being lost to the fluid because we're swirling up the fluid, and that's actually creating friction in the fluid, heating it up. And that is taking energy out of the body as it falls. And so the energy, though, that's being put into the body is gravitational potential energy, because as it's falling down, it's decreasing its gravitational potential energy, and that's going into this viscous dissipation. Okay, so this expression for drag force is basically related to these vortices and how they grow and form. Okay, so that's what happens for a pretty simple body like a sphere. Now, I also dropped those thin metal disks into the fluid, and we saw there was a fluttering motion. That's very typical for a thin, rigid body like these playing cards. If you drop them through the air, you'll see some kind of flipping around and fluttering as they fall. And so some controlled experiments were done of this phenomenon in 2D. So they took a rigid metal card, and they confined its motion to just a 2D plane, and they looked at snapshots. And so as it falls, here's that side-to-side fluttering motion, similar to what we saw before. And as this card gets more and more dense, there's a transition that happens. Here's, again, a side-to-side fluttering motion that's a little more violent than the first one, and a little more violent still. And eventually, it does this end-over-end tumbling motion. That's actually what's shown in this last picture here. And so as it does these different kinds of motions, that's going to affect the velocity at which it falls through the fluid. And the other thing to note is the velocity is not constant in time. So we talk about a terminal velocity. Normally, that's just a particular constant value. But as these objects move through the fluid, their velocity is changing in time. They're speeding up and slowing down. And that's because their dynamics is more complicated than that of a falling sphere. And here's a picture of the fluid as one of these objects is doing this tumbling motion. So here in white is a flat, rigid sheet that's falling through the fluid. And as it falls, it makes this track of vortices that you can see here. And so what I asked in my own research is, what happens if the body bends while it's falling? So you could imagine a sheet of paper that rolls up in some way as it's falling through the air. And what effect is that going to have on the speed at which this object falls, or where the object ends up when it hits the ground? So I'm really just interested in the basic physics of this fluid-body interaction. What can happen when you drop a flexible body in a fluid? So all these bodies I looked at so far were rigid. They didn't do any bending, okay? So now when you allow them to bend, more complicated things can happen. So here's an example of what can happen. So I imagine I'm taking a sheet of paper, say, and I'm dropping it at an angle to the vertical. And as I drop it, it's going to fall and create vortices in this sort of way that I've mentioned before. And so as it falls, it'll speed up to a certain speed. But then something kind of strange will happen. It'll basically reach a critical speed at which it starts to bend. And what's shown here, this black line, is actually a sequence of snapshots of that flexible sheet as it's falling. And so since it's falling along a straight line roughly here, you just see a continuous black line. But once it starts to bend down here, you can actually see the individual snapshots. And so the sheet is bending, and then the sheet actually starts to move upwards. So this can happen if you drop a flexible sheet. It doesn't actually just go straight down to the ground. It can actually go upwards at some times and then go back down. And so what's shown in this orange line is just the position of the sheet at one instant. So you can see the size of the sheet. It's not very large compared to the size of this frame. And these blue dots are the vortices that are coming off of that sheet as it moves through the fluid. So the vortices sort of trace the path of the sheet to some extent. And then when it comes down and does this bending motion and then moves off in a different direction, it sheds some vortices that have a spiraling pattern down here. And these vortices are more intense than the vortices up here. OK, so this is sort of a typical behavior of a flexible sheet falling in a fluid. So that behavior is shown up here in the left. I called it punctuated falling because it basically falls and then it bends, sheds vortices, and then it moves off in another direction, and then it will fall again, bend, shed vortices. So each time the falling is punctuated by bending. OK, other things can happen when you drop a flexible sheet, like a piece of paper, in a fluid. Here's a case where it does a very regular flapping motion. So it sort of meanders to the left and right as it's falling. And the vortex wake is this very regular pattern behind it. And then another motion is that the body will bend into sort of an arc of a circle, and it will spiral down in the circling motion as it's falling. And you can see this with a piece of paper, too. If you drop a piece of paper, sometimes it will get into this circling motion as it goes down. So what explains these different motions? Well, there are basically two important parameters. One is the density of the solid object relative to the density of the fluid. And so we already saw these in the terminal velocity, that the difference between the densities is important. Here, it's actually the ratio of those densities that's important. And the other important thing is the stiffness of the sheet. So this parameter B, I've called the bending stiffness. And as B gets larger, it behaves more like a rigid playing card. And as B gets smaller, it does more bending and does more violent changes in its motion. These different frames are showing trajectories of flexible sheets when I drop them in a fluid. I drop them from up at the top. You can see all these trajectories come together in sort of a dark clump up here. And so I'm originating all these sheets up there at the top. And then when I drop them, sometimes they do pretty crazy motions. They're just moving all over the place with a seemingly random behavior, but they are all going down on average. And the trajectories, though, have certain shapes which depend on how dense the sheet is and how flexible it is. So as I move around in this diagram, I'm changing how flexible the sheet is. So here the sheet's very flexible, and the trajectories have a very wiggly kind of shape. And over here, they're more stiff. And so you have more sort of straight lines in the trajectory. However, those straight lines are interrupted by a bending of the sheet. So eventually, the sheet falls so fast that it can no longer stay in a straight line. It becomes unstable to a flapping kind of motion. And when it does that flapping motion, it moves off in a different direction and eventually speeds up again. So that's what's shown in this movie. So the orange object is the sheet. And the blue object are vortices coming off that sheet. So sometimes the sheet goes up, but eventually it'll come to a stop because it is more dense than the fluid. And then it falls back down again, speeds up, and eventually it gets going so fast that it can't stay straight, and it flexes and bends. And when it bends, it slows down. Because when it bends, it has a bigger area that it's moving through the fluid with, and so there's more drag on it. And so the more drag on it, that's going to slow it down. And so it never can actually fall faster than a certain speed. OK, so there are some common aspects to how these flexible sheets move through fluids. And this is one of them. It basically speeds up, becomes unstable, and then it does this oscillation. But there is still a certain amount of apparent randomness to its motion in terms of the direction that it moves in. OK, so now I'm showing sheets that do a flapping behavior. So that's different from what I just showed. So these ones, they're a bit more flexible than that other one. And as they fall, they just do a steady flapping motion and shed vortices in a regular or somewhat irregular pattern. And so these sheets also have an instability to bending in the fluid. So they also don't want to remain straight, but they're flexible enough that they'll just keep bending at the right frequency so that they don't move off in sort of random directions, but rather they just fall straight down through the fluid. OK, so this behavior, the fluttering of these sheets as they fall, is known as the flapping flag instability. So this is an important instability in the field of how fluids interact with structures. And this is important if you're an aeronautical engineer trying to design the wing of an airplane so that it doesn't start oscillating in an airflow, which was a very important issue in the early days of aeronautics. This is also an important issue if you're a civil engineer designing a bridge in a windy place. So this is a famous instance of a fluid body instability. So the Tacoma Narrows Bridge near Seattle was built, but unfortunately it had the wrong properties for where it was located. The typical wind speeds actually excited an oscillation in this bridge, a twisting oscillation. And the bridge would start twisting in a wind. And the more it twisted, the more the wind made it want to twist. So it would start to oscillate in a certain way. And that oscillation would feed back to the fluid forces which were acting on it in a way that made it twist even more. And eventually, the bridge was actually destroyed by this twisting motion. So there are some nice videos of that you can see online. So this twisting of the bridge has a lot of similarities with that flexible sheet I just showed you falling through the fluid. They're both related to an instability of a flexible body in a fluid flow. And as the body starts to oscillate, that affects the fluid forces on the body in a way that can make it oscillate even more. So here's a flexible body that's sort of like the sheet I was showing you. It's a nylon thread in a soap film. A soap film is a thin sheet of fluid falling down, and the nice thing about a soap film is you can visualize the fluid pretty easily because it's in a 2D plane. So as the fluid's falling down, the soap film has a different thickness as you move around in it, and that makes these different patterns of light and dark when you shine a certain light on it, light with a certain frequency. And so that the light and dark allows you to visualize the thickness of the soap film in different places. And it also allows you to visualize vortices that form in the soap film. So these vortices change the thickness of the fluid, and so you can actually see them coming off of this flexible sheet, this nylon thread in the soap film. OK, so what happens here is I have the nylon thread, I make my soap film, and fluid is falling down past the nylon thread. And the nylon thread will just stay straight if the fluid doesn't go too fast. But if the fluid starts to go above a critical speed, then this thread will oscillate side to side in a very regular pattern. The flow is actually coming from left to right instead of up to down. But here's the nylon thread, and here's the vortices coming off of it. And so when I have a flow that's fast enough, you get this very nice, regular oscillating pattern of that thread. And this oscillating pattern actually has a lot of the same physics as the Tacoma Narrows Bridge and airplane wings as they flutter. So we've looked at the properties of this oscillation in a lot of detail. Here's a simulation of a similar phenomenon. So this is just showing snapshots in the simulation of the sheet, or flag we call it, and the blue dashed line are vortices that are coming off of the sheet. And vortices have this natural tendency to roll up into these spirals. So when you have a sheet that's oscillating in a fluid, it actually has a drag force on it. Like if you see a flag that's flapping on a windy day, it's putting some force on the flagpole that's holding it in place. Otherwise, it would just blow downstream with the fluid. And so, so the forces that are on a flapping object depend on how it's flapping and the vortices that are coming off of it. And so you can look at some interesting aspects of these forces when you actually put two bodies together, two flags or two flexible sheets, one behind another. So this is the same soap film that I showed before, but now I have two nylon threads, one behind another. And so when I have the soap film falling at a certain speed, what happens is the nylon threads will start to oscillate. However, they're influenced by the presence of each other. So if I put I put them in a tandem configuration, so one of them's right behind the other. The one that's behind actually oscillates a lot more than the one that's in front. So the one that's in front is somehow inhibited from oscillating by the presence of this thread, nylon thread behind it. And if I move them farther away, then the one in front is less inhibited from oscillating, so it does sort of what it would do on its own. The one behind, though, is still oscillating a lot more than the one in front. And the reason for that is the vortices. So vortices are coming off of this object in front as it's flapping, and you can see those vortices down here. And they're impinging on the object behind. So here's the object behind when it's close to the object in front. Here's the object behind when it's further away from the object in front. And you can see those vortices are colliding with this object. And when they collide with the object, they can make it oscillate even more. And so what this basically tells us is that when you put flexible bodies in a flow so they interact, they don't actually do a drafting behavior where the object behind has less drag because it's sort of hiding behind the one in front, but they do an inverted drafting behavior. So the object behind actually gets more force than the one in front because of these vortices. So that's a feature of flexible objects that are flapping in a fluid. Unlike a fixed object, like imagine a bicycle rider in a fluid, they can draft off of each other because they're a rigid object. They're not oscillating side to side, and so the vortices that come off are different. So in this experiment, they looked at the forces, which is the drag, and the amplitude of flapping, and they found that there were some peaks in these quantities as they changed the separation distance between the two objects. So as they increase the separation distance, the flag behind will flap harder and the force will be higher. That's actually shown down here. And then as they move them farther and farther apart, all these quantities tend to certain values, which are just what these two flags would do if they were in isolation, not affected by each other. OK, so what's going on here is the interaction between these two objects. And so I did some simulations of this because it's a lot easier to vary these parameters in a computer simulation than it is in the experiment. So the parameters of interest are basically the spacing between these flags and how flexible they are. OK, so what I found in the simulations was similar to the experiment, although there was one thing that was new in particular. And that was that sometimes the flags would flap in a very regular way. And if they flapped in a regular way, the vortex wakes would sort of roll up together. So there's a vortex wake from the green flag in front. There's a vortex wake from the orange flag in back. And they roll up together into this coherent wake. So you get one spiral here and one spiral here, combining the vortices of both flags. However, if I move that orange flag a little further away, you don't get this coherent wake. Instead, you just get a chaotic wake. So the vortices don't roll up into those nice spirals. They just do something less regular. And so there's actually a sequence of these kinds of coherent states like this. The next one is shown down here. And these irregular states like this. The next one is shown down in the fourth frame. And so there's actually an alternating sequence. They go from a coherent flapping together to an irregular flapping to a coherent flapping to an irregular flapping. And the reason for that has to do with the spacing between the flags. So these vortices want to have a certain spacing between them. And if the flags are going to disrupt that spacing, that creates a chaotic flapping behavior. But if the flags are spaced in the same way the vortices are spaced, then the vortices can roll up together and they're happy. They can make a coherent wake. However, the consequence of that coherent wake is a higher drag on this trailing flag, this orange flag here. So if you want to have less drag on this flag, in fact on both of the flags, you should place this flag in such a way that it actually disrupts the wake from the flag in front of it, so that you don't actually get the coherent wake of the two flags. OK, here's a movie of the coherent wake. So at first, the flags are doing something kind of funny, but they gradually settle down into this very regular flapping motion. Flag behind is flapping more than the flag in front, but the wakes are rolling up nicely together. And now they're spaced further apart, and the wakes don't roll up nicely together. The flag in front is still flapping nicely up and down in a regular way, but the flag behind is doing this very irregular motion, and consequently, the vortices cannot form nice, simple, alternating patterns, but they do something very chaotic. OK, so even though this motion is more chaotic and irregular, the drag on this flag is actually less than it was in the other situation. So we're basically just interested in the fundamental physics of these fluid-body interactions. There may be some principles here that could be applied to how fish school, but that's really a different situation than this. A fish, first of all, is not as flexible as these objects. Some fish fins can be quite flexible, but the fish body is a fair amount stiffer. And the geometry of the fish is also somewhat different. Fish is a three-dimensional object. But nonetheless, what we're learning from this is basically how flexible bodies interact with vortices and what the forces on them are. And some of these same principles could apply to a swimming fish in a fluid. OK, so I've shown you three kinds of examples of flexible bodies interacting in fluids: freely swimming foils, terminal velocity, and the dynamics of falling flexible sheets, and the flapping and synchronization of coupled flags in a fluid. OK, so I guess one of the main themes of these studies is how bodies can produce vortices and how they can interact with the vortices that they produce to have either large or small forces, depending on the situation. OK, so I'll stop there and take questions. Thank you.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.